y'all, welcome back to another round of chemistry notes. In this video, the last video of Unit 2, we are going to talk about the mole, which is abbreviated MOL. Yes, really, is the SI unit for amount of a substance. It's kind of like dozen or pair. These are both words that describe a number. So dozen describes 12 things, and a pair describes 2 things. Just like that, a mole describes a number of things. It describes the number of particles in exactly 1 mole. That's known as Avogadro's number. Not avocado, Avogadro. Avogadro's number is the number of things in 1 mole. That number, that magical number, is 6.02 times 10 to the 23rd particles. Right, so a dozen is 12, a pair is 2, and a mole is 6.02 times 10 to the 23rd. We say particles because this applies to all kinds of different things. Just like you can have a dozen cookies or a dozen eggs, or you can have a pair of shoes or a pair of earrings. You can have a mole of anything you can count. You can have a mole of it. So notice that we've got 1 mole is equal to 6.02 times 10 to the 23rd particles. Recall that if you can write it as a statement of equality, this equals that, you can use it as a conversion factor, which is exactly what we're going to use moles for. So talking about particles, before we get into actually using this, talking about particles, there are, and this should say 4 main types of particles. In Unit 2, we largely are going to be talking about atoms. Starting in Unit 3, we're going to talk a whole lot about ions. And then in the third 6 weeks, we're going to start talking about molecules and formula units. But there are plenty of other things you can count. In these notes, we're going to count protons. You could count puppies. You can count books. Anything you can count, you can use a mole for. If you could talk about it in dozens, you can talk about it in moles. So, as we use these 4 conversion factors, the same rules we've always learned are still going to apply. Start with what you know. Multiply by a fraction. What goes up must come down. Here we go. First example asks, how many moles are there in 6.53 times 10 to the 24th atoms of gold? An atom is one of our particles that we learned. So we're going to start with what we know. We're going to start with our 6.53 times 10 to the 24th atoms of AU, atoms of gold. Start with what you know, times a fraction. What goes up? So our atoms of AU, what goes up must come down. So we'll bring our atoms of AU down. We're trying to convert to moles, so we'll bring moles of AU up. And we just learned a conversion factor for this. We said that 1 mole is equal to 6.02 times 10 to the 23rd of anything, in this case atoms. So when we fill this in, it's going to be 1 mole and 6.02 times 10 to the 23rd atoms. And at this point, you're going to plug it into your calculator. Remember that the safest way to plug this in is to replace your times 10 to the, replace that with the E. Remember, you get the E from second, comma. So you would type in 6.02 second comma 24 divided by 6.02 second comma 23. And when you do that, your calculator should tell you 10 0.847176, which is of course not our final answer because we need to round it for sig figs. Remember that this fraction here is a conversion factor, and if it's a conversion factor, it does not affect your significant figures. So the only number that affects our significant figures is this one right here. We started with 3 sig figs. We did a little multiplication. We need to end with 3 sig figs. So this answer right here is going to round and become 10.8. So that is our number. The units, we were asked for moles. Moles are in the top of our last fraction. So our units are moles of gold. Moving forward in the year, most of your answers are going to have 3 parts. They will have a number, they will have a unit, and they will have the thing you are talking about. So 10.8 moles of gold. That's your full answer. Let's look at another one. Number 2 says how many atoms are in 2.75 moles of xenon. So once again, we will start with what we know, 2.75 moles of xenon times a fraction. What goes up, moles of xenon, must come down. So we'll bring moles of xenon into the bottom. We're trying to get to atoms, so we'll put atoms of xenon in the top. Same as before, between moles and atoms, it will be 1 mole is equal to 6.02 times 10 to the 23rd atoms. So typing this into your calculator, you'll get 2.75 times 6.02 times 10 to the 23rd, and that will tell you, well, your calculator will say 1.6555 E24. Make sure that if your calculator is giving you an E something at the end of your answer that you include that, because if you do not include this E24, your answer is wrong. Not kind of wrong, but just wrong. So we need to include our E24. We're going to rewrite it a little bit, and we need to round for sig figs. We started with 3 sig figs, so we need to end with 3 of them, which means our answer will round to 1.66. That E we're going to rewrite as times 10 to the 24th. Then our units are atoms, and we are talking about xenon. So there's our answer to number 2. Number 3 is going to use the same skills, but it's going to be just a little bit different, just a little bit more involved. So number 3 says how many moles of neutrons are in 2 moles of carbon-13. Well, our first step here is to find out how many neutrons are in 1 atom of carbon-13. So to do that, we'll take our mass number, 13, subtract away our 6 protons. If you look on your periodic table, carbon has an atomic number of 6, so it has 6 protons. 13 minus 6 is 7. So what that means is that 1 atom of C13 has 7 neutrons, is equal to 7 neutrons. And since we can write this as a statement of equality, we can use it as a conversion factor. So now we're going to work through this problem. Here we have 2 moles. We're going to start with what we know, which is 2 moles of carbon-13. What we know times a fraction. What goes up must come down, so we'll bring moles of C13 down. Before we can get to neutrons, we have to figure out how many atoms we have. Neutrons are a smaller piece, so we need to find the larger piece, the atoms, before we can go to the smaller piece, the neutrons. So first we'll convert to atoms of C13. Once again, 1 mole is 6.022 times 10 to the 23rd atoms. And now we can do times another fraction. What goes up, atoms of C13, must come down. And when we started the problem, we said that 1 atom of C13, we can get to neutrons. So we'll put neutrons in the top. 7 neutrons are in 1 atom just atom, of C13. And if we were just looking for the number of neutrons, we would be done. But we are not just looking for the number of neutrons, we're looking for moles of neutrons. So we need to do times one more fraction. What goes up must come down, so neutrons will come down. Moles of neutrons will go up. Oops, gonna run out of room. And just like anything else, a mole of anything is 6.02 times 10 to the 23rd of that thing. So 1 mole of neutrons is 6.02 times 10 to the 23rd neutrons. And now we're ready to plug this into our calculator. This will be 2 times 6.022 times 10 to the 23rd times 7 divided by 6.022 times 10 to the 23rd. When you plug that in, you're going to end up with 14. Rounding this 4 significant figures, because we started with only 1 sig fig, we are going to round this to 10 moles of neutrons. You may see a shorter version of this. You may see a little bit of redundancy, and if you do, that's great, but you need to be able to show your work. Please do not look at this problem and say, oh, it's going to be 2 times 7, there's my answer. I have to see your work on this. So if you wanted to cut out a step, if you can make this leap, which some people can, some people cannot, you could have solved this problem as 2 moles of C13 times a fraction. What goes up must come down. But now, instead of going to atoms and then back to moles, we could say that in 1 mole of C13, there are 7 moles of neutrons. And that is how you could skip all of those other steps and still get your 14, which rounds to 10. But if this 1 mole is 7 moles of neutrons, if that step does not work for you, don't try to make it work. Just use the longer version. It'll always be safe. So again, you will always and forever have to show this work on a free response question. If you do not show your work, if you just write down a number, I cannot give you any points. That is 0 points. So now you're going to have a chance to practice on your own. In your book, you've got 3 problems to work on your own. Notice that the third problem is not asking you for moles of protons. It is asking you for protons. So you're not going to do that last fraction where you convert from protons to moles of protons. You're just going to leave it as protons. So when you're ready to check your work, unpause the video and check it out. And there is a typo on this slide. So number 3 is not 10 moles of neutrons. Number 3 should be 5.2 times 10 to the 25th protons. Accidentally copied down the practice answer instead of the example answer instead of the practice answer. So number 3 should be 5.2 times 10 to the 25th. If you are not sure where these answers came from, hop on over to my website, look at the full key so you can see the steps written out. If you did well on this, then go ahead and keep going. We're going to learn a second conversion factor, which is molar mass. It's really creatively named. The molar mass is the mass of 1 mole of a pure substance. That's the molar mass. It is written in units of grams per mole written that way, or grams per mole written this way. Yes, these are the same thing, but for some reason, some people will see it one way and not understand that these two mean the same thing. So G/mol, or actually grams over moles, mean the same thing, and it is read as grams per mole. So those are your units. To find the molar mass, it's pretty simple. The molar mass of an element is numerically equal to the atomic mass, or the average atomic mass of that element. And the atomic mass, remember, is the decimal value from the periodic table. Not the whole number at the top of the little box, but the decimal number at the bottom. That's the atomic mass. So this is true for most elements, but it does not apply to your diatomic elements. You have 7 diatomic elements. They are bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. These are diatomic, di meaning 2, atomic meaning atoms. They're diatomic because they will never exist as a single atom. If they show up in a compound, they act just like normal elements, but if they're out by themselves, they're going to use the buddy system. You'll never have just one atom of bromine. It's always 2 bromines together. You will never have one atom of fluorine off by itself. It'll be 2 atoms together. You're going to want to memorize these now because your life will just be better for it. So one way to memorize them is to read this like a word, to read it as Brinkelhoff, and each letter represents an element. If you look at the back of your booklet on your periodic table, you'll notice that 6 of these elements, bromine, iodine, nitrogen, chlorine, oxygen, and fluorine, actually make a 7 on your periodic table. And then hydrogen is also included. So whatever helps you to remember, you need to be able to pick these out in a problem. All right, so let's look at some molar mass examples. Example number 1 here says, what is the mass of 1 mole of uranium? Well, if you go look on your periodic table, you'll find the square for uranium, and it's got, the symbol for uranium, which is U. Underneath that U, it has 238.03. Up until now, we've been talking about that as the atomic mass. But if we're talking about a mole of something, it's also the molar mass. So this will be 238.03 grams per mole are the units there. Same with scandium. Go find scandium on the periodic table, and you'll find that the molar mass, the mass of 1 mole of scandium, is 44.96 grams per mole. So with regular elements, really easy to find the molar mass. For diatomic elements and compounds, it's a little bit trickier. For these, you're going to need math. You're going to need to add or to multiply, depending on what you're looking at. For example, our first example here says, what is the molar mass of molecular oxygen? Molecular oxygen means it's not in a compound, it's just O2 doing its O2 thing. Well, here you can see it's 2 atoms of oxygen. So to find the molar mass, we'll do 2 times the mass of 1 oxygen atom, which is 16.00. This is from your periodic table. And then 2 times 16 is 32.00 grams per mole. So pretty easy for your diatomics. Just 2 times the mass of 1 atom gives you the mass of 2 atoms. Number 2 says, what is the mass of 1 mole of glucose? And it gives us the formula for glucose is C6H12O6. Well, the mass of glucose is going to be the mass of 6 carbons and 12 hydrogens and 6 oxygens. So to find it, that's exactly what we're going to do. We'll do 6 times the mass of carbon, which is 12.01, plus 12 times the mass of hydrogen, which is 1.008, plus 6 times the mass of oxygen, which we already said was 16. Again, this is the mass of 1 atom. So then when you plug it into your calculator, 6 times 12.01 plus 12 times 1.008 plus 6 times 16, your calculator should tell you that the molar mass of glucose is 180.16 grams per mole. Just add up all of the atoms that are in that compound and you will get the mass of the compound itself. So if you know the thing you're talking about, if you know the element or the compound, you can find molar mass this way. If you do not know those things, you can still find molar mass if you are given a mass and a number of moles. So for example, we have a 2 mole sample of an element is measured to have a mass of 61.94 grams. What element is it, and how do you know? Well, molar mass is in units of grams over moles. So to find our molar mass, we'll take our number of grams, our 61.94 grams, and we will divide by 2 moles. Plugging that into your calculator, 61.94 divided by 2 is equal to 30.97 grams per mole. But this is not a dimensional analysis problem. There are no numbers we get to ignore here when it comes to significant figures. So we did some division, means we should look at our total number of sig figs no matter where they are. This number on top had 4, this number on the bottom had 1, so our answer needs to be rounded to 1 sig fig. So this will round to 30 grams per mole as our answer. And then as far as what element it is, we'll go to your periodic table and start looking at the masses, start looking at those decimal numbers under the symbol. Find the one that falls closest to 40. That should come out to be phosphorus. And in fact, if we had not rounded our answer for sig figs, the mass we found would have been exactly the mass of phosphorus. So we know it's phosphorus because they have the same molar mass. So molar mass, just like density, is an intensive property. It can be used to identify things. All right, last bullet here. Because molar mass can be written as a fraction, it can be used as a conversion factor in dimensional analysis. Just like we used Avogadro's number to go back and forth from atoms to moles, we can use the molar mass to go back and forth from grams and moles. So our first example here says how many grams are in 2.00 moles of chlorine. When you see chlorine, it should set off some warning bells in your head because chlorine is one of your diatomic elements. If we're talking about chlorine, it is Cl2, 2 atoms of chlorine. So we're going to work this just like any other dimensional analysis problem. We'll start with what we know, 2.00 moles of Cl2 times a fraction. What goes up must come down, so moles of Cl2 will come into the bottom. We are looking for grams of Cl2, so we'll put grams of Cl2 in the top. And since we are comparing grams and moles, this is where we want to use the molar mass. So the molar mass of chlorine is going to be 2 times the mass you see on your periodic table. It'll be 2 times that 35.45 to give us a molar mass of 70.9 grams per mole. Put another way, there are 70.9 grams in every 1 mole of Cl2. So to fill in our fraction here, we'll do 70.9 grams in 1 mole of Cl2. Then you can multiply, and 2 times 70.9, your calculator is going to tell you that that is 141.8. Be smarter than your calculator. This fraction is a conversion factor. It's not going to affect your sig figs, but we did start with this number. It does affect our sig figs. There are 3 sig figs here. We need 3 in our answer, so we are going to round this to 142 grams of Cl2. You need your number, you need your unit, and you need the thing you're talking about. That is your answer. We'll do one more like this. Example number 2 is going the other way. It says how many moles are in 78.2 grams of C6H12O6. We already found the molar mass for this compound in an earlier example. The molar mass of glucose is 180.16 C6H12O6. So we're going to work this problem just like every other dimensional analysis. Start with what you know. We have 78.2 grams of C6H12O6 times a fraction. What goes up must come down, so grams of glucose will come down. Moles of glucose will go up. then we will fill in our numbers. This is the molar mass, which means that in 1 mole of glucose, there are 180.16 grams of glucose. So we'll fill in 1 mole and 180.16 grams. When you plug that into your calculator, 78.2 divided by 180.16, your calculator is going to say 0.434059. That's going to round to 3 sig figs here, 3 sig figs in our answer. This will round to 0.434 moles of glucose, moles of C6H12O6. We have a number with correct sig figs, we have a unit, and we have the thing we are talking about. So that's our answer here. All right, the last thing we need to do in this video is put it all together. You can use Avogadro's number and molar mass in the same problem. In fact, it's pretty common to use them in the same problem. So when this happens, all the steps are going to remain the same. All the same rules still apply. Start with what you know, times a fraction, what goes up must come down. It's just that they're going to be more fractions and more units. So I've got a little roadmap for you here. Notice that moles are in the middle and atoms and grams do not touch each other. It is impossible to go directly between atoms and grams. You have to go to moles first. Moles are like your base unit. Remember when we were doing metric conversions, you'd always go to your base unit between your different prefixes. You would go from like centimeters to meters and then to kilometers. Same thing here. You have to go through moles before you can go to atoms or grams. So last thing on this slide, remember between atoms and moles, that's where you're going to use Avogadro's number. That's where you'll use your 6.02 times 10 to the 23rd. Between moles and grams, that is where you'll use your molar mass. And then if you're going between atoms and grams, you'll have to use both of these things in order. All right, here we go. Our first example says how many grams are in 1.20 times 10 to the 24th atoms of zinc. So we're trying to go from grams to atoms or from atoms to grams. We don't see moles in this problem, but we have to put moles here because moles has to be in the middle between atoms. We'll go atoms to moles and then moles to grams. So let's go ahead and set this up. Step 1, start with what you know. 1.20 times 10 to the 24th atoms of zinc times a fraction. What goes up must come down, so atoms of zinc will come down. We are trying to find grams in this problem, but we cannot go straight there. We have to go to moles. So we'll put moles of zinc in the top. Between atoms and moles, it will always be 1 mole and 6.02 times 10 to the 23rd atoms. Not quite done. We are looking for grams. We only have moles, so we'll do times another fraction. Once again, what goes up must come down. We'll bring our moles of zinc to the bottom. Now we can go to grams. We know how to go between grams and moles. That's with our molar mass. So the molar mass of zinc, what is the molar mass of zinc? The molar mass of zinc is 65.39 grams in every 1 mole of zinc. So to fill in our conversion factor, we'll do 65.39 grams in 1 mole. Now this is set up to give us grams of zinc. We wanted grams of zinc. We'll plug this into our calculator. You'll do 1.20 second comma 24 divided by 6.02 second comma 23 times 65.39. And what your calculator is going to put out is 130.3455. We need to round this for significant figures. This fraction is a conversion factor. It doesn't matter for sig figs. This fraction is a conversion factor. Nothing in it matters for sig figs. The only thing that matters is this number right here. We started with 3 significant figures. We need to end with 3 significant figures. But here's the problem. If we round this, to 130, well, that's only 2. And if we round it to 130.3, well, that's 4 sig figs. So we need to call this 130 point. This is how we get 3 sig figs. It's a little weird, but it's 130 point. Don't put anything after the decimal point. And the units are grams, and we are talking about zinc. So this is 130 grams of zinc. All right, last problem. Here we go. All right, problem number 2, or example number 2, says the recommended daily intake of potassium for adolescents and adults is 4,700 milligrams of potassium. How many atoms is this? So this problem, we're starting with milligrams. We don't know how to go anywhere from milligrams. We don't know milligrams in moles. We don't know milligrams in atoms. What we know is how to get from milligrams to grams. That is something we've been doing since school started. From grams, the only place we can go is moles. And then once we have moles, we can move on to atoms. So this is sort of our roadmap of how we're going to work this problem. Each arrow here represents a conversion factor. Each arrow represents a fraction. So we're going to start with what we know, just like always, 4,700 milligrams of potassium, which is K. So 4,700 milligrams of potassium times a fraction. What goes up must come down. Milligrams of potassium come down. So we're going to go to grams first because that's the only place we know how to get from milligrams. So we'll put grams of potassium on top. Grams are bigger than milligrams. So we'll do 1 gram, which is 1,000 milligrams. So that'll give us grams of potassium. And now we're sort of back on track with problems we've been looking at. We'll do times another fraction. What goes up, grams of potassium, must come down. And we're trying to go to moles next, right? We cannot go straight to atoms, even though that is what we are looking for in the end. We're going to have to go to moles first. So we'll do moles of potassium in the top, and this becomes a molar mass thing. So in 1 mole of potassium, looking at your periodic table, you can see that there are 39.10 grams of potassium in 1 mole of potassium. That'll give us moles, but we are looking for atoms, which means we need 1 more fraction times 1 more. What goes up, moles of potassium, must come down. We can convert that to atoms of potassium. Once again, if it's moles, it's going to be 1 mole. The number of atoms, that's Avogadro's number. Particles, things you can count, that's Avogadro's number. So that'll be 6.02 times 10 to the 23rd atoms of potassium. And now it's time to plug this into the calculator. 4,700 divided by 1,000 divided by 39.10 times 6.02 second comma 23. When you type that all into your calculator, what you should get is 7.236317 E22. Do not forget to look for this E22 at the end of that calculator line or your answer is going to be wrong. as a general rule, if you're talking about a number of atoms, it's probably going to have some scientific notation because atoms are not very big. You need a lot of them. So rounding this for sig figs, we started with 2. We should have 2 in our answer. This will become 7.2, so 2, times 10 to the 22nd. This E22 means times 10 to the 22nd. Atoms of potassium. So that is our answer to this one. All right, next up in your book is practice. You've got quite a few practice problems. They're all mixed. Some of them are atoms and grams, some are atoms and moles, some are grams and moles. It's just all over the place. So take a few minutes, work 1 through 10. When you're ready to check your work, unpause the video. All right, hopefully this is what you got as your answers. If it is not what you got, go on over to my website, look at the key so you can see each step worked out, see if you can figure out where you went wrong. If you did get these all right and you're feeling good, it's time to wrap up that second quest and start studying for your test because this is the last material of Unit 2. So good luck and happy studying.